This is a video for AQA Discrete Mathematics. Simplex Method, section 2.3, where we're looking at setting up the Simplex Tableau. Here's a linear programming problem with decision variables x and y. We're looking at a two-variable case at the moment because it's easier to explain what's going on with the method to look at a graph at the same time. So we have, in this particular case, three constraints, three non-trivial constraints, which are given here, and then of course the non-negativity or trivial constraints x is greater than or equal to y and y is greater than or equal to 0. And we know from our experience previously that the optimal solution will be at one of the vertices. The first thing we do, as we've already discussed, is to introduce the idea of slack variables. So for this case, where we've got three constraints, we're going to need three slack variables, S1, S2 and S3, so that our inequalities become x plus y plus S1 is equal to 12. The second one, 2x plus 3y plus S2 is equal to 30, and the next one, 2x plus y plus S3 is equal to 20. And that then introduces three more trivial or non-negativity ones, which is S1 is greater than or equal to 0, S2 greater than or equal to 0, and also S3 greater than or equal to 0. Having done that, the next step is to look at the objective function p equals 10x plus 9y, and to write that with the variables x and y on the left hand side, so p, x and y. So that will give us p minus 10x minus 9y is equal to 0. So in total now 4 equations. The first one for the objective function, and then the other ones with the slack variables looking at the three constraints. Now each of the vertices we're looking at then has some of those variables x, y, S1, S2 and S3 equal to 0. So for example, at the origin we know there that x and y are both equal to 0. Moving up the y-axis, so leaving x equal to 0, we reach this point here, which is on the equation which is given by the second of the equations there, second of the slack variables. So that's where S2 is equal to 0 and also x is equal to 0. Looking at this point, we have that S2 and S3 are both equal to 0. This one, we have S1 and S3. And finally, the one here where we've got y equal to 0 and also S3 equal to 0. So you can see that each vertex has two of those variables equal to 0. There are other vertices. For example, we could take this one here, where x equals 0, and we also then have that S3 equals 0. But that one is outside of the feasible region. And we'll see how, when we apply the simplex method, we avoid reaching one of these vertices which lies outside the feasible region. To use the simplex method, however, we don't actually need to consider the graph, and what we do first of all is to put all of these equations into a table. So this is what is called the Simplex Tableau, and you can see along the top we have got the different variables p, x, y, s1, s2 and s3. And the first thing we do is put in the coefficients of each of those variables for the equation, starting off with the objective function at the top. So we'd have 1p minus 10x minus 9y, and then zeros for s1, s2 and s3, and the right hand side is the value of that at the moment, which is 0. Similarly for the second equation, 0p, 1x, 1y and 1s1, put 0 for s2 and s3, and a value at the moment of 12. The next one is 0 for p, 2 for x, 3 for y, and 0 or 1 for s2, 0 for s3 with a value 30. Finally, 0 for p, 2 for x, 1 for y, 0, 0, 1 for s3, and then a value of 20. That's the completed Simplex Tableau, which has come from, remember, taking our linear programming, which was written in terms of inequalities, changing those inequalities into equations by introducing slack variables. Remember that we must write the objective function with the variables on the left hand side and then equal to 0 initially, and this gives us then the coefficients that are entered into the tableau. In the next video we'll consider how we then manipulate this tableau